Hello, you're welcome. All right, so now we are going to be talking about sound. Okay, so sound wave. All right, so in our last video we discussed the general wave characteristics. Okay, so sound is a type of wave that is being produced by a vibrating body. Okay, which of course the sensation of stimulate the sensation of hearing. Okay, so when body vibrates, okay, they definitely produce sound. So sound is always um, produced by a body that is set, okay, that's set in vibration, right? Even air that actually transfers sound to your ear actually vibrates, okay? So it is the vibration of the air that actually transfer the sound from a source to your ear. And of course, the ear is actually known as the detector of sound. Detector of sound. So because inside the ear you will have there are uh organelles that actually uh vibrate, okay, based on the sound impulse it receives, and that vibration is being interpreted, okay, because there's a connection from the ear to the brain. All right, so which of course translate and interpret the vibration that enters into the ear, okay, and actually give the sound, and of course the interpretation of the sound. Okay, so that just by the way. All right, so in this tutorial we're going to be talking about basic terms, okay, which of course illustrate the concept of sound. So we will begin. All right, so I'll be taking some notes, then I'll bringing it to the screen. All right, so now we are going to start by talking about the propagation and the velocity of sound. All right, so I bring it up to the screen. All right, so here we go. All right, so I'm gonna take it to the screen. Okay, so propagation of sound. Sound is a mechanical wave. We've actually talked about that, okay, which requires material medium for its propagation. So sound can either travel in a solid, liquid, or can pass through air, okay. So please take note of that. So it needs material medium, and that's why it's called a mechanical wave. Now, velocity of sound. Now, the velocity of sound depends on the medium it propagates. All right. Now, when sound travel in solid, it travel fastest. Okay. The speed of sound is greatest. Okay. Uh, when it travel through solid, solid gives it the maximum speed. Okay. Then it is being followed. Now, of course, in solid you have a velocity of almost, okay, approximately 5,000 meter per second. All right. In liquid, okay, it's followed by liquid, which of course approximately in liquid sound travel at the velocity of 1,500 meter per second, and of course in air an approximation of 330 to 340 meter per second. All right, so which simply means that the velocity of sound, okay, actually increases, okay, as matter changes from gas. All right, the medium changes from gas to liquid. All right, then to solid. So please take note of that. All right, so now we are going to actually look at this velocity of sound, okay, the factors that actually affect the velocity of sound, the velocity of sound in air. Now, velocity of sound in air. So we're going to look at the factors that actually affect it. Now, when sound travels through air, all right, definitely the velocity of sound in air is actually being affected by the absolute temperature. So by relationship, we know that we have that the velocity of sound in air is directly proportional to the square root of the absolute temperature. What does this simply mean from this relationship? Okay, it simply means that velocity depends on absolute temperature. When the temperature increases, okay, when the temperature actually increases, okay, the temperature of air increases, definitely um the velocity of sound also velocity increase. Right, so we can actually create a relationship, right? We create a relationship, a formula here that will help us analyze this. All right, so here we go. So we have velocity being proportional to the square root of the absolute temperature. Now if we change the proportionality to equal to, we introduce a constant. If this should actually be changed to an equal to, we introduce a constant k. So now which simply means that the constant k is going to be equal to v all over the square root of t. All right, so which simply means that the ratio of velocity divided by the square root of the temperature is constant. So if that simply means that anytime there's a change in state, okay, as temperature changes, velocity will change. So let's say the initial state is v1 all over the square root of t1. Okay, so when there's a change in state from initial state to final state, it will still be in the same ratio. Okay, it will still be, so this time around that is v2 all over the square root of, okay, t2. So please take note of that. So we use this relationship to denote, okay, the relationship. We use the relationship to denote how velocity depends on temperature. And of course, this temperature here is the absolute temperature. Capital letter T is absolute temperature. And of course, absolute temperature is a temperature that is measured in Kelvin. Okay? And of course, that is just a unit of temperature. And if you are being given temperature in Celsius, to convert it to the absolute temperature, you know what to do. I hope you know that. Okay, let's say you want to convert temperature, okay, to Kelvin, temperature in Kelvin. If the temperature was given in Celsius, theta degrees Celsius, all you need to do, okay, add the temperature in degrees Celsius, okay, to 273, or add 273 to it. You've converted it. For example, now if the temperature is 27 degrees Celsius, so if I want to convert it to Kelvin, all right, all I just need to do is the Kelvin temperature will be 27 plus 273. So that gives me 300 Kelvin. All right, so now let's look at a typical example. Okay, we'll solve some question. Excuse me, I'll bring some question on the screen, and we'll do justice to it. All right, so now still talking about the relationship between velocity of sound and of course the temperature. So we have a question. The velocity of sound in air is 20 meters per second at 27 degrees Celsius. So the initial velocity according to the question is 20 meters per second. And at that point the initial temperature is 27. Don't forget I need to convert this, okay? I convert it by adding 273 to it. Alright, so the question is now what will be the velocity? What will be the velocity when the temperature now? What will be the final velocity? That's V2, okay? Question mark. When the temperature T2, the final temperature is 37. We'll convert to Kelvin, right? By adding 273 to it. If I add 273 to this, that's 300 Kelvin, and of course this should give me 310 Kelvin. Okay, so don't forget our relationship. V1 all over the square root of T1. Alright, initial temperature and initial velocity, alright, is equal to V2 all over the square root of T2. Alright, putting our values, we have 20 divided by the square root of T1. The square root of T1 is 300. Square root of 300, of course, V2, that's what I'm looking for. T2. 310. So all I just simply need to do is just to cross multiply here, alright? Cross multiply, of course, that'll be V2 multiplied by the square root of 300, right? Is equal to 20 multiplied by the square root of 310, right? Divided by the square root of, okay, sorry. So that means V2 now. So this one will now be division, right? The square root of 300, 20 times the square root of 300 divided by the square root of 310, please pardon me, 310, okay? Divided by the square root of 300. So I hope. So you just simple you use calculator to do this, okay? Square root of 300. Okay, maybe let me help you do that. So let me get my calculator myself. The calculator myself, okay? So we do the square root of 300. Then if we do the square root of 300 multiplied by 20, right? So square root of, excuse me, square root of 310 first. Square root of 310, then multiplied by 20. It's approximately 352. It's approximately 352. Then divided by the square root of 300. Okay, so what's the square root of 300? So 300 square root. So approximately 17. So I have 17. Alright, so 352 divided by 17. 352 divided by 17. What do we have? So 20.7 approximately. So the velocity, the final velocity of that sound is 20.7. All right, now there are other factors that the velocity depend on, but I'm just going to take some few. Okay, I will talk about the others, okay, in our next video, but I'm just looking at the factors, okay, that affect the velocity of sound in air. So we talked about temperature. Then the next thing I'm going to talk about is wind. Basically, wind affects the velocity of sound. All right, now look at the whole idea, okay? Wind actually, because sound travels, okay, through air, and of course wind also is affects air, because wind can actually move air to a particular direction. Of course, you know that it blows air to a particular direction. So if wind can influence air, definitely wind can also influence the velocity of sound in air. Look at the whole idea. Now when wind and sound is moving in the same direction, okay, so this is sound, okay, so let's see, this is wind. If they're moving in the same direction, the wind tends to suppress the sound, okay, and actually cause it to, okay, to bend downward. And of course, if the sound bends downward, there's this tendency that the intensity of the sound will increase, okay, the audible intensity will increase to the listener, to the hearing of the listener. But a situation where the sound, okay, and the wind travels in opposite direction. One thing is for sure, the wind will definitely cause the sound to bend upward. Okay, so here we know that the intensity increases. All right, intensity increases, but in this case intensity of the sound reduces, and of course intensity deals with power. Okay, that will also reduce the velocity, right? Because power is connected, has a relationship with velocity. We know that power in physics is always given as force times velocity. All right, so if intensity, this actually is related to power of a sound. So when the intensity of the sound increases, the velocity increases. When the intensity of the sound reduces, the velocity of the sound reduces. Okay, so these are the basic thing. Okay, basic factors, all right, that affect sound in air that I just illustrated. We are going to talk about the factors that affect sound in solid and other medium, but let's actually get the basic concept, okay, the vital concept first that will help us solve examination question, right? So let's proceed with our notes. All right, so we're gonna talk about a very important concept, all right, which of course is echo. Important concept of sound, which is echo. So I will clean up my screen, and so echo of a sound. What's an echo? Echo is defined as the reflection of sound. All right, you know that sound is a wave, so it undergoes reflection. Okay, so echo is the reflection of sound which causes it to be heard again after some interval of time. So sometimes you actually hear some sound, okay, repeating itself from a source, especially in the areas where people are using a dressing system and there's a big hall that is close by. Okay, sound tends to enter into that place, and of course it reflects and you hear that sound all over again, echo back. All right, so that phenomenon is actually common. Now sound is reflected as it encounters a wall or obstacle. All right, so and every wave actually does that. Once they get to a place where they encounter a wall, they tend to reflect. Now what I'm going to actually look at, let's say this is sound, the source of sound. Okay, source of sound, and let's say this point is a boundary or the obstacle. Now this sound is being released, it reaches this place, it returns back, then it is being heard again, right? Let's say the distance it takes for it to reach this place is x, so it also moves the same distance backward. And let's look at the time. Okay, the time for it to be heard to be equal to t. All right, the s here is the distance it travels. All right, so now you discover that this sound, the total distance, okay, it travel is 2x, s plus x. Okay, so I can actually evaluate the velocity of the sound, which of course the displacement s plus x, that's 2x. Remember, velocity is always displacement all about time or distance all about time. Okay, and how you want to look at it, then divided by the time it takes. So the time it takes for it to go to and fro, that is, I used it to represent that. All right, so this formula is the formula for the velocity of an echo, so please take note of that. All right, now the question is, what is the application of an echo? Okay, so we're going to look at different application that echo actually brings. Okay, of course, one of the application of echo is we use echo to determine the depth of a sea. Echo can be used to determine the depth of a sea. How does that happen? And we'll illustrate that. Okay, so one good application of echo is number one, determination of the depth of a sea. Okay, let's say you will not, of course, the depth of a sea can be very long, and of course, you may not want to go down to measure it, all right? Say you have water body. All you just need to do is just to, okay, with your boat. Okay, let's say this is your boat. So okay, so you just need to release sound all the way to the bottom. Okay, then use your time. Set your time. And of course, the sound reaches to the bottom of the sea. It returns back and is heard again. All right. So of course, knowing that the velocity of sound in liquid is 1,300 or 1,500 approximately. Just once you know the velocity of sound in that liquid, all right, you can now apply this formula. V is equal to 2x, all right, all over t. The time for you to hear the echo is this t. So you can now rearrange the equation so that the depth of the sea now being x is going to be equal to vt all over 2. So that is it. That's one application. Okay, then another application is you can also use it to determine the shoal of fish. Right, inside the sea, there's areas where you have, okay, fishes actually habit, right, where they cluster this shoal of a fish. Right, so some other application which of course you need to go, all right, research yourself as we proceed. Okay, so we'll proceed. Let's just get the basic information because we are going to solve questions. All right, okay, so now we're going to look at sound in terms of noise and music, because really sound can be classified in terms of either a noise or it's a muse, or either it's pleasant or it's unpleasant. Okay, so that means the one that is actually pleasant, that is not pleasant, is actually referred to as noise. Okay, now the one that's pleasant can be music, right? And of course it can be, okay, so music, generally music is a sound with a regular coordinated frequency, and of course it's pleasant to the ears. All right, so some sound has regular coordinated frequency, but when a sound, okay, has an irregular and of course an uncoordinated frequency, it becomes a noise. Why? Because what makes it a noise is not just that it's uncoordinated, okay, it's because it is not pleasant to the ears. Okay, either based on its intensity, all right, of course the intensity of the sound. Now that's intensity of sound, okay, that is actually the range that the ear can actually handle. Okay, now there are some intensity of sound. When the intensity of sound actually passes the range, okay, the ear can handle, it becomes, okay, the intensity becomes, because it actually causes pain to the ears. All right, and at that particular level that sound is unpleasant, right? Or the sound comes irregularly, okay, it just not really coordinated, so that is noise. But generally, okay, we look at the characteristics of sound, right? Now sound possesses the following characteristics, so that's what you're going to be talking about. A sound can be measured based on its pitch. Now each of these characteristics of sound, you should know exactly what they depend on. All right, now the pitch of a sound, the pitch of a sound depends on its frequency. So high pitch, high frequency. When someone actually um, says that he sings a high pitch, it simply means that the person's frequency, okay, is very high. So the higher the frequency, the higher the pitch. Please take note of that. And of course, in the scale of music, okay, you move from a lower pitch, okay, to high pitch. So please take note. So pitch of a sound depends on its frequency. All right, then of course the quality of a sound. Now the quality of a sound is the characteristic of the sound that makes it possible for one to differentiate sound of same frequency but coming from different sources. All right, now let's say the sound is of the same frequency, but you can differentiate when probably a violin, the sound is, the music probably is from a violin, okay, and of course violin, then flute, though they play the same frequency, are you okay, but the quality gives them the quality excuse me, okay, quality give them different flavors. And of course, what does the quality of sound depend? Okay, quality of sound depends on the factors. Please take note of all these factors, okay. It depends on the factors known as harmonics or overtone. Okay, we'll talk about harmony and overtone, okay, later. All right, so please take note of pitch depend on frequency, quality depend on harmonics or overtone. Then others, we have loudness, the loudness of a sound. Okay, when you increase the volume of a sound, right, you're increasing the loudness. And of course, the loudness of a sound depends on the amplitude of the wave. Okay, every sound is a wave and has amplitude. Right, so when the amplitude of that sound increases, its loudness increases. Okay, then of course, the last but not the least, intensity of the sound. Okay, intensity of the sound is talking about how the flow of energy for per unit time, flow of energy per time. Okay, so the rate of flow. So the rate of flow of energy is already per unit area, per area, sorry. The flow of energy, okay, per area of a particular surface. So the rate of flow of energy. So intensity is the rate of flow of energy. Of course, rate of flow of energy is energy all over time, right? Then divided by the area, per unit area. Energy all over time is power. So invariably now I can simply say the intensity of sound is the power that sound delivers per unit area. Okay, so that is going to be watts per meter square. That's intensity. We use symbol I to represent intensity of a sound, right? So the amount of power it delivers per unit area is referred to as the intensity of a sound. So please take note of that. Okay, so now we'll talk about another important term, okay, which of course is known as reverberation. Reverberation of sound. Now reverberation is simply, okay, multiple echo. Multiple echo, okay, which actually stretches, okay, in a long duration, okay, that makes it look as if it's just a sound, just one sound, but it is the combination of echoes, all right, that comes in interval, okay, to one another. So just simply reverberation is multiple echo, right? So please take note of that. Now, Okay, so let me actually delete this. Okay, excuse me. Okay, so we know that sound passes through solid, right? And of course it passes through liquid, and it passes through gas, it passes through air, right? Now solid air, the vibration of sound in solid and of course in air can actually create, we can use it to create a form of musical instrument. For example, if you want to actually play drum, okay, is a musical instrument that belongs to, okay, the instrument type known as percussion. So different types of drum, are you okay, is percussion. And of course, when you hit on a drum, you are vibrating a solid. Drum is solid. All right. Then when you blow air into flute, all right, you are actually vibrating air. All right. And all these actually create what is known as musical tone. Musical tone. All right. So now we are going to start with one of air. Okay, let's look at how musical tone is actually, okay, gotten by the vibration of air. Vibration of air column. All right. So now that's what we're going to be looking at. Now, in produce vibration of air column to produce musical tone, okay, there are two. We use pipe. You blow air into a pipe, okay. So there are two pipe which, of course, we are going to use. We have a pipe that is closed at one end, known as closed pipe. Then B, we have open pipe. So we're going to start with this first, which is closed pipe. Right. So as the name implies, okay, it's simply a pipe that is closed at one end. Okay, if I should draw that, or better still, right? It's closed at one end. So now air can actually be set into vibration inside this pipe either by blowing into it or use a turning fork. All right, when you use a turning fork, you will actually have the air being set. As the turning fork vibrates, the air actually vibrates inside the pipe and vibrates. Okay, each vibration actually generates, of course, you know that is sound in air. All right, it's always a longitudinal wave. Okay, so since this is within just inside a pipe, it's inside a pipe, it's inside the pipe, it's not progressive, so it is longitudinal stationary wave. Okay, so whenever air column inside a pipe is actually set into vibration, okay, the air vibrates to produce a longitudinal stationary wave, right? Then of course the vibration doesn't just vibrate, okay, it doesn't just create a vibration, it actually creates a tone. So we have what is known as resonance. Okay, resonance is where we now hear a tone after a vibration creating a tone that is audible. Now what is resonance? Okay, resonance is a process by which a medium, okay, vibrates in its fundamental frequency. Okay, the vibration of a medium, okay, at fundamental frequency. And due to the impulse, okay, due to the impulse it actually receives impulse, it receives from a vibrating body. So which simply means that this air inside this pipe doesn't just vibrate on its own. Something is actually called vibrating that actually induces this vibration. It's either you actually use a turning fork, okay? As the turning fork vibrates, it excites the air inside to vibrate, or you blow air into it, okay? Blow air into it, and of course it vibrates. So at the point where the vibration, the source of the vibration, okay, causes the air inside, okay, to vibrate at what is known as fundamental frequency, then of course resonance occurs. And at the point where resonance occurs, okay, you now have here what the loudest. That's where they have the loudest sound. And that loudest sound comes in form of a musical tone. So the loudest sound first is said known as the fundamental frequency, the first loudest sound. So which simply means that if we are dealing with vibration of air, okay, in a pipe, what we need to find out is what is the fundamental frequency that is produced at resonance. How do we get that? Okay, so now I'm going to actually derive that. I draw my pipe again. Okay, so I have this wave like this, okay? Please take note of this. This is always going to be the node, right? The close end of the pipe will always produce the node. But it's a stationary wave, of course, I told you a stationary wave, that is going to be the node, okay? The length of this pipe, which of course is still the length of the air column, I use L, okay? L to represent the length. All right, so this is the node, and of course you know that this point is the antinode. So anytime a closed pipe is set into vibration, the closed end will always produce the node, while the open end, okay, is the point of maximum, which is always the antinode, okay? And I told you that the wavelength between the node and the antinode is always a quarter wavelength. So that means this length, the length of this air column, or the length of the pipe, okay, in terms of wavelength, will always give you quarter wavelength. So the length of this pipe always is, once this air is set into vibration, is always equivalent to quarter wavelength. So if it is equivalent to quarter wavelength, that means if I cross multiply, right, and I have that, the wavelength is going to be equal to 4 times the length, 4L, okay? All right, so now remember all I'm doing here is for me to find fundamental frequency, the very first frequency, all right? The very first tone that's set at resonance, known as the fundamental frequency. How do I get that? V is equal to lambda F. Don't forget this formula. So frequency now being V, right, all over wavelength, it can now be equal to, for a closed pipe, that will be V. And of course, my wavelength is 4 times the length of the air column, 4L. Okay, so this is what we know as fundamental. I use F0 to represent it, fundamental frequency. So the first frequency, very first frequency is known as the fundamental frequency, and the formula is given as V all over 4L. Okay, now if every other frequency after it, every other resonance that occur after the very first resonance, okay, is will produce higher frequencies, okay, above the fundamental frequency, and those higher frequencies is what is known as harmonics or overtone. All right, so we simply mean that if I know the fundamental frequency, this is the formula for the fundamental frequency of a closed pipe, okay. To get the harmonics are simply the multiples, okay. Harmonics are higher frequency, which is are odd multiples. They are all odd multiples. Of course, you know what odd numbers is. Odd multiples, okay, of fundamental frequency. Right? So if they are odd multiples of fundamental frequency, which simply means that if I know my fundamental frequency, which of course I use F0 to represent, I can get my harmonic. So I can get my first, second harmonics. So for first harmonics, okay, is the next odd number. The next odd number, okay, that I have apart from 1, all right, is 3. That is 3 times. So first harmonics, okay, is 3F0, of course, which is something as 3V. F0 is already V all over 4L. So please take note of that. Now the second harmonics is going to be equal to, what's the next odd number apart from 3? That's 5. 5F0, which of course is 5V all over 4L. So that is how you get your harmonics, okay. Of course, this is the fundamental frequency. Okay, so I'm gonna look at, let's get question that we could actually if there's a question that we can solve to illustrate this, okay. Okay, so here I have a question, excuse me. Okay, I'll clean up the board. Okay, so here we go. So the question goes like this: if the length of a column in a closed pipe is 20 meters, evaluate the third and fourth overtones of the vibration. All right, so this is a closed pipe, right? So we're looking for the third. Don't forget that the first is equal to 3F0. All right. Second. So we're looking for the what? We're looking for the third and the fourth, right? Second is 5F0. So now the third is 7F0, which of course is 7 times the velocity, 7V, don't forget 7V all over 4L. That's the formula, okay. F0 is V all over 4L, so that's going to be 7 times VV. Here is given as 340, right? Okay, then divided by 4 times the length of the air column. The length of the air column is 20 meters, right? So as easy as that, so you can use calculator and evaluate that. Is, of course, the fourth is the next odd number. Of course, the fourth harmonics is 9, all right? So that's gonna be 9 times whatever you have as the fundamental. So it's as easy as that. Okay, so let's proceed. So we'll talk about it, how we'll talk about it on open pipe, right? Okay, so I bring it up to this screen. Okay, so now this is a closed pipe. Let's look at how the vibration works in an open pipe. Okay, now don't forget an open pipe, okay, is so called because the pipe is open at both ends. All right, as you can see here, this is an open pipe. Okay, so if it's open at both end, remember open end will always give you antinode. As you can see, this antinode, this antinode. So this is where it is the middle that gives you a node. All right, so now if we should analyze this now based on our wavelength, of course, from here to here, this is the length of the pipe, which of course is the length of the A column, that is L. So if we should analyze this based on our wavelength, okay, don't forget that since I have two node to antinode, from node to antinode, you already know that the wavelength is quarter wavelength. So I have quarter wavelength for this side, and of course another quarter wavelength. So when you add quarter plus quarter, all right, so the total wavelength, are you okay? The total length was quarter wavelength plus another quarter wavelength. So you know when we do this, LCM is 4, right? 4 divided by 4 is 1. 1 times lambda is lambda. 4 by 4 is 1. 1 times lambda is 1. Okay, so I have 2 wavelengths, 2 lambda divided by 4. When this divide, you have 2 cancels of 1. So I have 1 lambda all over 2. So that means the length of the air column for an open pipe is always lambda all over 2. Okay, so that means to get the wavelength now, I cross multiply, right? So I'll give 2L. So my fundamental frequency, remember the first frequency I get is fundamental frequency, which I represent by F0. Okay, so of course, how do I get the F0? Using velocity. Okay, that'll be velocity divided by lambda, which of course is velocity all over lambda, which is velocity all over 2L. So this is the formula for the fundamental frequency of an open pipe. Okay, so please take note of that. Then the question is, what happened to the overtones? Okay, the multiples are all integers. All integers, okay? Not just odd integers. All integers. So I can now simply say that, all right, 2, 3, 4, of course you're not counting odd or even, you're counting all, right? So the first overtone or harmonics is going to be equal to, right, 2, because the fundamental is already 1, right? So others are multiples. 2. Second is 3. So that's how it goes, right? So please take note of that, all right, as we proceed. Okay, so now we talked about air, so we're going to look at vibration in string, all right, in a string instrument or string that is fixed at both ends. Vibration in string. Okay, now when a string is fixed at both ends is set into vibration, it produces a fundamental and overtones, the same as open pipe. Now there's actually a system, okay, an experiment that is used to illustrate vibration in a string. Okay, it is just simply made up of a hollow bus, a bus, okay, a bus with a string that's attached to it. a boss with that has knife edge, okay, attached to it, and a string is being connected to the two knife edges, right? Like a guitar. Now the idea of the boss is that it's like a guitar boss is to magnify the sound. Now when I plug this string, I will start hearing a tone. Why? Because there's going to be a vibration, okay? And of course this vibration, you know what type of wave is it? Okay, it's a wave which of course is stationary. Of course is stationary. So the wave I have here, that's by the vibration of this string, is stationary first, and of course it is transverse. Stationary and transverse. All right, so the boss makes the sound to be magnified. So if you look at it critically, okay, the very first, the end of the string always give you node. That's node, okay. Remember, from node to anti-node is quarter. From anti-node to node is a quarter. So 2 node to, so that definitely will give you half, okay. So the length of the string from here to here, the length of the string, okay, is always half, which of course, you remember in an open pipe, okay, that we treated, the length of the string is still half, okay. So that is why we said that every both the fundamental frequency that you got, all right, which is for an open pipe V all over 2L, and of course the overtones, okay, 2F0, 3F0, okay, is applicable to a string set into vibration. So we don't need to go through that again, all right. So whatever you have for an open pipe, but there's something that we need to actually discuss, okay, when it has to do with string, right, that's set into the vibration. Especially that's where the string instruments, guitar, actually is being constructed from, okay. All right, so remember, that's one thing you should know. When you plug the string, okay, it actually vibrates. Then you adjust the length. When people play guitar, they'll give different tone, right? Why? Because as they're plugging their right hand, okay, it's actually plugging the string. Their left hand is actually placing their hand on the fret, just to actually change the length of the vibration, okay. So different fret that you put your hand, okay, to reduce the length of the string gives you different frequency, and of course it's different scale. So that is simply means that there's a relationship that exists between the frequency that you get in a vibrating string and the length, and that's the relationship we're going to look at from this formula, okay. So for a vibrating string, we can simply say that the frequency of the vibrating string is given by the formula 1 all over 2L, the square root of T all over M. T is the tension of the string, M is the mass, okay, mass that is on the string, right. So of course this is 1 over 2L. So now this is the formula, but this formula shouldn't be it shouldn't be an issue, right? Because I don't really need to discuss or use this formula, okay, everything in this formula. All I just need to do is just to create a relationship. I told you that whenever this is frequency and of course this is length, they are inversely proportional to each other, okay. That simply means that the frequency of a string is inversely proportional to the length. The lower the length, the higher the frequency, and of course frequency is also goes with pitch, right. That is why someone that is actually playing a guitar string, if he wants to play octave, okay, he will bring his hand closer to reduce the length, okay. So this point, when the length is reduced of the string, then of course you have higher frequency in form of octave, all right. If you want to reduce the frequency, you increase the length, bring your hand to the neck to make give you a longer length of the string. Okay, so we can simply say that for a string that is set into vibration, that is producing music, the frequency is inversely proportional to its length. And of course, if you look at what we have also, we can say the frequency is proportional to the square root of the tension. So the more the tension on the string, the more it increases the frequency, and the frequency is inversely proportional to the square root of the mass. All right, so please take note of this. Okay, those are basic concepts, right? And of course, we'll look at questions. Okay, we'll definitely look at questions. So we talked about string instrument. Of course, like we can just discuss that finally, and we are good to go. All right, so musical instrument. All right, musical instrument is divided into string instrument, which of course we talked about. Guitar is a string instrument, piano is a string instrument. Okay, I know that some of you are asking, piano, how, where is the string in piano? Now the piano we are talking about is actually the oldest piano. All right, that once you press a key, the key actually is hit on a string. That's a kind of lever that causes the key that you press to hit on a string to produce a sound. Of course, violin is also a string instrument. Then for wind instrument, you have trumpet, saxophone, flute, okay, and the likes. They use this vibration of air to produce sound, and of course, drums, vibration of solid, okay, different types of sound. That's called, they call them percussion instrument, all right? So that is just sound for you. We'll look at uh some formula and of course exam questions. Okay, so that we'll do that in a jiffy. All right, see you.